Hey everyone, welcome back. So in this video, we shall take a look at the concept of joint stationarity. So we are going to see under what conditions are two different time series considered to be jointly stationary. So this is an extension of the concept of stationarity. So two time series x and y are jointly stationary if each are stationary and the covariance function depends only on the lag. Lag is the distance between the 2 points. So if the time series are jointly stationary, then the cross correlation will also be a function of the lag, right? Because if the cross covariance is a function of the lag, then the cross correlation will also be the function of the lag. So this is how the cross correlation will look like, right? So xy means we're looking at two series. So this is the cross correlation. H means that it's a function of the lag. So here is an example. So Wt is white noise. Xt is Wt plus Wt minus 1 and Yt is the difference between the two terms. The question is, are Xt and Yt jointly stationary? So if you recall the definition, we first need to verify that x and y are stationary by themselves, and then so let's see. So if they are, so for them to be stationary by themselves, we need the mean to be constant. So remember, we're talking about weak stationarity. It has two conditions. If the mean is constant, and if the covariance or the autocovariance function depends only on the lag. So the first condition can be checked here. Expectation of x and y are both 0 for all time points. So this is a constant. So next we need to see if the autocovariance is only a function of the lag, right? And after we verify this, we shall see if the cross covariance is also a function of the lag. But first we'll look at the autocovariance. So we'll start with the x time series. So this is the covariance between xt and xt. So the lag here is 0. So if you substitute the expressions for each of these, you can see that when you open out, two of these would survive, right? So there is a Wt here, these are common, and Wt plus 1, Wt plus 1. So both of these have two terms in common. So two terms will survive. So it will be 2 sigma square. If you look at, so the distance between the 2 points is now this minus this is minus 1, or the distance between them is 1. So if you substitute the terms, you get a single sigma square, and if you go 1 time point ahead, you'll see that it's again sigma square, and if you go 2 time points away, if the distance is 2 between the 2 time points, then xt and xt t plus 2 will have nothing in common, and the covariance will be 0. So we can summarize it this way. So gamma xh, so you can think of h as probably this minus this, so t, right? So t plus 1 minus t. So this is the distance between the 2 time points. So if the h is 0, it's 2 sigma square. If h is plus 1 or minus 1, it's sigma square, right? And 0 if it is greater than 1, right? If the distance between the 2 points is greater than 1, then it's 0. Similarly, you will find that covariance function of y has the same form. But except that the covariance here, there's a minus sigma square instead of the sigma square. So here, instead of writing, so distance, so h is plus 1 or minus 1, because it depends whether you're going 1 time point ahead or a time point front, right? So I'm not just looking at the distance, I'm subtracting the 2 time points, and you will see why. So anyways, from here we can see that the series is stationary, right? Because this just depends on the distance, right? Look at the cross covariance terms. So covariance between xt and yt, you plug in the expressions. Remember to be careful about the signs. So covariance of WT is sigma, and this is sigma square, so this will cancel out and be 0. So don't ignore the signs. If you were to ignore it, you would get a different answer altogether. Now, if you look at covariance between xt and yt minus 1, so I'm going one time step back here. So this turns out to be sigma square. Xt and yt plus 1 is minus sigma square. So even though the distance between the 2 points is 1, right, it kind of matters, right? Here it's tt minus 1 and tt plus 1. Each of them has a different value. So it is still a function of the distance, but the order matters. So more than distance, I will say that this is a function of the difference, or the difference between the 2 points, or the lag between the 2 points. Because when you say distance, the sign doesn't matter, and that was true for a lot of the examples we saw so far. But here, let's just use the word maybe difference or lag, right? Because the order matters. In any case, so if you go, so to summarize, right? So if the difference between the 2 time points is 0, the cross covariance is 0. If the difference is 1, so now if I do t minus 1, right? So the difference between these two is 1, so it's sigma square. If I do this minus this, the distance is minus 1, or the difference is minus 1, so it's minus sigma square. And if you take a lag greater than 2, you will find that x and y have no terms in common, and it is going to be 0. So this example is slightly different than most of the examples you've seen so far, in the sense that the sign of this lag plays a role. However, it is still dependent only on the lag, right? The actual value of t is not playing a role here. So we will conclude that the series are jointly stationary. Okay. So we first verified that each of the terms are individually stationary, and then we looked at their cross covariance function. So that's all for this video. Next, we shall take a look at how to estimate correlations for time series, right? So far we've analytically calculated what the formulae for the covariance or the correlation should be. Next, we'll see how to estimate that from an actual data set. So I'll see you next time. Bye.